Hey, good evening, everybody. Since we're still not able to meet together in a classroom setting, I thought I would experiment with trying to put together a recorded PowerPoint presentation. So this is the first one. This is on chapter 6 in the textbook. Um, Let me first start off by saying there's a lot of good information in this chapter about fixed film processes, and I would highly recommend that you do the reading and follow along in the OTGO workbook. And just this video is just going to briefly cover some of the highlights in the reading that I think you really ought to focus on. And as we go along, I'll try to put together more of these and put these up as YouTube videos on our YouTube channel, and hopefully we can work through the class remotely until we're clear to meet together again in the classroom. So let's go ahead and get started. Uh, Fixed film systems are also known as attached growth systems. Uh, this is part of secondary treatment. Uh, we've already talked in the class about preliminary treatment, which would have been, of course, grit removal and screening. Primary treatment, which would have been the chapter about primary clarification, where we remove all of the subtlable solid material. Secondary treatment is where we treat that primary effluent. Even though we've removed all of that solid material, we still need to remove dissolved, uh, non-subtlable solids, uh, and that sort of thing. So there typically are two types of secondary treatment. Attached growth, which we're talking about right now, and then suspended growth, which is another term basically for the activated sludge process, which we'll be covering in a couple weeks. So uh, attached growth or fixed film, we're typically referring to the trickling filters and rotating biological contactors. I know in the chapter there's towards the end, there's some material about membrane bioreactors and that sort of thing, mobile bed reactors. Those are more of like hybrid secondary treatment systems, I would say. There is a component of attached growth in that the organisms do attach to a media, but at the same time, they're also partially uh, oxygen, at least, is supplied through aeration. So I tend to look at those as more of a hybrid than a true attached growth system. So I won't be covering too much about those in this PowerPoint. Um, Trickling filters, of course, there are lots of diagrams and better pictures in the textbook than I can reproduce here, and this is not my picture, so I do know how to spell distributor correctly. Um, but the main takeaway here is that trickling filters do not actually filter a wastewater. The idea of the trickling filter is to provide a media, some sort of media that provides surface area for the microorganisms to grow and attach themselves to. And then we trickle water through that media and expose uh, those microorganisms to oxygen through airflow through the voids in the media. And then that pollution that they use basically for food for their life processes at the same time. So the idea of trickling filters and that media is to create a large surface area for this growth to take place, and then lots of voids, lots of space in there to allow for airflow. Um, so I would say in this chapter, pay special attention to the four components of trickling filters. This might be a question that you would see on a licensing exam. Those four components would be, of course, the containment structure, basically the walls of a tank or a vessel where a trickling filter media is held. The distribution system, of course, as you read in the text, those can be either rotating arms that are powered by the flow of water through those rotating arms or through fixed nozzles located on the surface of the trickling filter. The third component would be the actual filter media itself, which for the most part would be some sort of plastic or resin or some sort of material like that. Some of the older filters do have rock media, but those are getting rarer and rarer as they get retrofitted for plastic media. The plastic media is able to provide a lot more surface area. They're much lighter, uh, lots more void space to allow for airflow. And then finally, the last component would be the under drain system. So wastewater flowing from the top of the filter down to the bottom is going to be collected in that under drain system and then moved on to secondary clarification. Trickling filters, another thing that you want to take away from this chapter is the four basic classifications: low rate, intermediate rate, high rate, and roughing filters. The nitrification towers that I've listed here at the bottom, I'll talk a little bit more about that in a minute. But as far as classifying trickling filters, focus on the top four. These are all based on organic loading, so that's why we need to measure our primary effluent. Say BOD would be the primary measurement, that biochemical oxygen demand. So when you're doing the math problems, trying to calculate pounds of BOD per 1,000 cubic feet, that's where that would come in as far as organic loading. And there would be different design specifications based on the size of the filter. Low rate, intermediate rate, high rate, and roughing filters. Also keep in mind with roughing filters and probably most high rate filters, those filters are not designed to remove all of the pollution that's being fed to them, all of that organic loading. Typically those are going to have another, either another trickling filter or maybe conventional activated sludge following after them to finish up treatment of that flow. Also, be aware that with the trickling filter or the rotating biological contactor or the secondary treatment, you're going to have secondary clarifiers. The microorganisms are going to slough off the media after a while, and those sloughings are almost create like a trickling filter sludge that has to be removed from treatment, but before you can discharge your final treated effluent. So this diagram here kind of points out just kind of like a cross section of the microorganisms. You can kind of see right there at the surface of the media, as the slime layer builds up, it's going to get a little bit thicker and thicker, and the organisms on the very outside here are exposed to oxygen as well as the waste that they use as food for their biological processes. Meanwhile, as the layer gets thicker, these microorganisms that are closest to the surface of the media are no longer getting oxygen or food, and after a while they're not going to be able to stay attached to that media, and that's where sloughing occurs. And as pieces of that microbial slime, as pieces of those fall off that media and get washed down into the under drain. Those are the sloughings that have to be removed in secondary clarification. So this is designated as a facultative process. Facultative is a word that you'll, if you don't know already, you want to be familiar with that word. That basically means that these processes are both aerobic and anaerobic. Facultative basically would mean both aerobic and anaerobic. We'll be talking a little bit more about a facultative process when we get into discussing ponds and treatment lagoons. So a little bit about operational strategies for trickling filters. Just be aware of this, that they can be operated in parallel or in series. In my little diagram here, I guess the first circle here would represent like primary clarification. And from primary clarification in parallel, if you had two filters, half the flow would go to one and half the flow would go to the other. You're going to split that flow in half and load those filters evenly. Um, at the same plant with the same setup, you could also possibly operate them in series, where all of the flow from the primary clarifier would go to one filter, and then from that filter to the second filter, and then from there to final clarification. So uh, sometimes these plants can be designed with a little bit of flexibility like that, so you can operate them either way. And then I've outlined a couple of hypothetical situations where you might operate in parallel and then switch to series or vice versa. Um, Generally, I would say probably switching uh, from series flow to parallel flow, maybe in a high flow situation, to minimize hydraulic loading to each filter as much as possible. And then in an opposite situation of switching from parallel to series flow, it might possibly be advisable if you had advanced warning of a toxic slug load coming into the plant, where you might try to operate them in series and put all of that toxic load on one filter and not the other to try to hopefully maintain some of the microorganisms in the second filter to allow you to go back to full treatment after that slug load passes through. So a couple hypothetical situations where you might switch from one to the other, but definitely be aware that of parallel operation versus series operation and what that means. As far as troubleshooting, quite a bit more detail in the textbook, so I won't spend a whole lot of time on this. I would say these are probably the top three situations as far as troubleshooting trickling filter operation, and be aware that a couple of possible solutions to all three. Ponding and filter flies, flooding the filter by closing off the under drain system and allowing the filter to fill up. That's a pretty common way to try to remedy that situation. As far as ice accumulation, I know the book says, oh, cover the filters. I mean, that's not always practical if you don't have covers to just say, hey, let's just get a cover for it. Something that you can do that's quick and dirty would be to reduce the recirculating rate. Um, Probably also something to mention that they do cover in the textbook as far as recirculating flow through the trickling filters. That's pretty common. And you would do that to maybe even out hydraulic loading, to reseed the filter with microorganisms and get more complete treatment in the flow by pumping some of that flow back through the filter all the time. And then, of course, the last one would be odors. I would say a big one with odors would be to check the ventilation system. A lot of these trickling filters have to have supplemental ventilation, like some sort of forced air to force airflow through the filter, and pretty much on all these licensing exams, if it mentions odors, your first thought has got to be, is this thing going septic? And if it's going septic, either A, are we holding uh, the wastewater too long in one place, which might be a way to remedy that would be to increase recirculation, or is it not getting enough oxygen? And in the case of a trickling filter, in that case, you might want to check your ventilation system. And then finally, a little bit about rotating biological contactors. Pretty similar to trickling filters. Rather than passing the water through the filter, in this case, you're passing the filter through the water. And these are not nearly as common as trickling filters. Just a couple things to point out about them. They work generally the same way. You're exposing microorganisms to the wastewater as it goes through the water, and then to oxygen as it comes out of the water and is exposed to air. And most of these are going to have covers to prevent damage to the media from sunlight, as well as to prevent excess sloughing from heavy rain. One thing that I don't think is mentioned in this version of the text that was in previous versions is what the microorganism slime should look like. And typically, any healthy wastewater system, they're going to tell you it should look kind of brown. And if it's gray, maybe that's not ideal. But like I said, not too many RBCs around, so most of the focus of the chapter, I'm pretty sure the text, or at least in the OTCO binder, is going to be on trickling filters. So that's all I've got for tonight. Hopefully, as we go along and I make more of these, I'll get a little bit better with the production value. But I'll go ahead and export this out to YouTube and get it up for you guys. So you at least have something to watch, and put one together for chapter for next week. All right. Good night.